All right. While the last few people are trickling in, I'm going to introduce our first speaker, who's Igor Chilingarian. He's an astronomer here at CFA in the optical infrared division, and he's been here since 2011. Igor got his PhD in 2006 from Moscow State University and the University of Lyon. He was then a postdoc at Paris Observatory and the University of Strasbourg. And his general interests are studying stellar populations in quiescent dwarf galaxies, as well as looking at their black holes. And he's also done a lot of work with the Virtual Observatory. Today, he's going to be telling us about searching for intermediate mass black holes and finding a population of them identified as low luminosity AGN. Take it away.
Okay, thank you very much for the nice introduction. I guess the mic is working, so. Okay, so this is the pointer, right? Okay. What I'm going to present you now is a project that we've been working on for a few years now, and I'm talking on. I'll be talking on behalf of our core team, with 3 Russian guys, one of whom is in France, and the others two are in Russia. Kirill is an undergraduate student, and those 2 are postdocs and researchers, because in Russia there are no postdocs, so people go to research right away. Anyway, so we have a distributed team. This is just a brief advertisement for in one slide, and we are in 3 places now. Like basically, one of our guys is now at NYU Abu Dhabi. He's a postdoc. Yeah, this is what I forgot to mention. And we focus on methodology using modern tools, data mining, virtual observatory, and data-intensive astronomy. What we are known for is the first discovery of compact elliptical galaxies. This was a paper in Science 2009. Then the discovery of isolated compact ellipticals, which we interpreted as runaway galaxies from clusters, which was Science in 2015, and discovery of the first X-ray pulsar in M31, which was APJ paper in 2017 by Ivan. And the study I'm going to talk about, it actually originated from a tutorial that we ran at the ADAS meeting in Sydney in 2015. ADAS is Astronomical Data Analysis Software and Systems. It's a conference series that goes every year all over the world. And I ran 3 tutorials at ADAS where we educated the audience on how to use virtual observatory tools and do use elaborated techniques for data analysis. So let's start with an introduction. What are intermediate mass black holes? This is all terminological, and the difference is like the boundaries of mass is what you consider like stellar mass black holes and massive black holes. They are all sort of conditional. It depends on who you're talking to. But generally speaking, most people would say that intermediate mass black holes is something that is heavier than 100 solar masses, because it's not a solar mass black hole anymore. You can hardly make a 100 solar mass remnant from a star. And it is less than 10 to the 5 solar masses, or a few times 10 to the 5, depending on who you're talking to again. And the upper mass, it actually has cosmological importance. And this is because right now we still don't know how supermassive black holes form in galaxy centers. We know that they should start from some sort of seeds. And depending on the physical origin of those seeds, you end with this mass or with that mass. So if you start with stellar mass black holes, you're starting with a really little black hole that you're supposed to merge, and then, well, you can grow black hole either by merging it with another black hole or by accreting material or swallowing star once in a while. Or you start with heavy seeds right away, which originate from direct collapse of gas clouds in the early universe. So basically a cloud that is 10 to the 5 solar masses or more, it collapses directly into the black hole without passing through the stellar stage. So there is little doubt that those black holes would exist because the first LIGO detection already went dangerously close to 100 solar masses. So if you put this as a threshold, it will be a little bit more and you're done. There is also an object, ESO 24349HLX1, hyperluminance X-ray source, that is considered the first solid IMBH candidate. It's an off-source, off-center X-ray source in a lenticular galaxy, and its flux is too high to be a normal ULX. However, there was this paper by King 2014 where there was an argument that it's actually a beamed X-ray emission, so we substantially overestimate what we're looking at. Then there was this object, RGG 118 by Rines and Greene, and this, however, had only 4 photons in the X-ray detection, so it didn't pass formal detection thresholds. And finally, there was a discovery of a black hole in 47 TAC, a tentative discovery. It was a Nature paper where it was found using stellar dynamics and pulsar timing. However, one should keep in mind that in the past, there were several claims about black holes in centers of globular clusters, and then all of them were refuted, except this one so far. Generally, there are 3 ways how you can search for intermediate mass black holes. You can look for low luminosity AGN. You can look for ultraluminous or hyperluminous X-ray sources as bright off nuclear sources in X-ray, or you can look in globular clusters using stellar dynamics. HLX search was started by Ivan a few years back. He basically formalized the search algorithm using SDSS and virtual observatory tools. You cross-match SDSS against XMM-Newton in this particular situation, and then you exclude the nuclear part. And then you end up with a population of sources which are within the optical radius of a galaxy, but not in the center. So, of course, as many of you might expect, most of those sources would be background quasars, which are there just on occasion. However, the estimate is that around 20% of those should be real. They identified a sample, and the follow-up program is going on. He had collaborators at Keck, and they took some data. They took some spectra, and all of them turned to be background quasars. We took like 3 or 4 with mirrors in near infrared, and they also turned to be background quasar. One was particularly interesting because it wasn't seen in the optical, just in the near IR, because it was a quasar that was projected right behind the star-forming region in a galaxy, so it was heavily absorbed. So you see it only in the K band, and in the optical it's like 25th magnitude. And in the K it looks like a supernova. Anyway, here I'm going to talk about nuclear IMBH. And what do we know about them? So this is a famous plot, which is velocity dispersion of the galactic bulge, or central spheroidal component, velocity dispersion of stars, and black hole mass on the y-axis. And if you plot normal galaxies with normal black holes, they form a well-known sequence. And actually, if you put low mass black holes, this was literature compilation like a few years back, they sort of reside on the extension of this relation formed by massive black holes. And we knew a few of them. Most of them were in the 10 to the 5 range, like they were above 10 to the 5, but below 10 to the 6 solar masses. And this is the 47 TAC with a black hole mass of 2,500, as far as I remember. And interestingly, if you plot it on the extension of this diagram, it falls right on. So, how we're looking for black holes. This is the schematic of the AGN phenomenon that helps us to discover them in big data sets. You have an accretion disk around a black hole with X-ray emitted by the accretion disk corona. it is surrounded by rapidly moving clouds in a pretty dense region, dense clouds in the region of hundreds to thousands of a parsec. For small black holes, it's smaller. For bigger black holes, it's bigger. This is a region where the velocity is hundreds to thousands of kilometers per second. And those clouds are too dense to emit forbidden lines. But they emit recombination lines. And this is how we see them in the optical spectrum. This is H alpha, and the broad component that you see, it's here, and it comes from those clouds. If you look at larger scale, you have a narrow line region. It's where the density is already low enough so that you can emit forbidden lines, and that's where narrow lines come from. So basically, if you look at forbidden lines in an AGN, they look just like narrow lines. Sometimes they have some sort of broad features connected to outflows, but we're not talking about them here. However, if you look at recombination lines, and if this region is not hidden from you by the dust torus, then you see the broad line component. And that's how we can look for low mass AGN. Why low mass? You can, of course, look for high mass as well. But what is interesting about the broad line region is that it allows you to estimate the virial mass of the black hole, because this region, this part is supposed to be virialized, not like the narrow line region. And this is exactly what we did. Our approach is conceptually similar to what was done by Greene and Ho years ago, but we made a very important improvement. When people normally analyze emission line spectra, they consider that an H alpha line or something like that, like a recombination line, would be a combination of a Gaussian broad line and Gaussian narrow line. However, the narrow line regions are not Gaussians. And if you force them to be Gaussians, you end up with strong residuals, fitting residuals, that actually hampers the quality of detection for the broad line region. We designed an algorithm that fits narrow lines non-parametrically. So basically, you can put any shape of the line in the spectrum. You can have double, triple, whatever, asymmetric. And then we try to fit all the lines in the spectrum together, all narrow components, and add broad line components for lines that we're interested to measure, like H alpha and H beta and H gamma. And this is a critical improvement, because here, when you're dealing with spectra like SDSS, which are sort of snapshot spectra, they're not very deep, and the spectral resolution is not very high. Those fitting residuals that you can end up with if you assume profiles to be Gaussian, they become critical, and they're killing your detection. So this is to demonstrate how it works. This is a non-parametric shape of the narrow line region, and it's what it looks like, and this is the broad line region that is approximated as a Gaussian. So the workflow, it's a massively parallel automated workflow to analyze 1 million SDSS spectra without any pre-selection on host galaxy properties, and using wavelengths, adding crucial information from large multi-wavelength catalogs. So we use optical, infrared, radio, X-ray, everything that we could get to. And we ended up with a fit stable with 200 plus columns that then you can filter and look for the stuff you're interested in. So the two main resources that we used is RCSED. It's our own project. It's reference catalogs of spectral energy distributions of galaxies. You're very welcome to visit this website and see what it is. It has UV to near IR fully calibrated SEDs. And the next resource would be XMM-Newton source catalog. Then we actually complemented it with Chandra source catalog and with Swift that release 1 catalog. This is the largest X-ray catalog so far, and here I'm talking about DR7, but in fact we redid the analysis with DR8, and it didn't reveal any new candidates because the improvement was incremental. So this is how the workflow works. We get analysis of spectra, so we take SDSS spectra, we fit stellar population models, subtract it off, then we analyze emission lines and look for broadline features. Then we use statistical criterion to say whether we get statistically significant improvement of the quality of fit by adding the broadline component. So here you see the same line fitted with and without broadline, and you can see the residuals are very different. Then we filter them out with some complex filter that I will show on the next slide just to frighten you. And this is, then we end up with a list of candidates. We try to get input from literature and input from the virtual observatory. Then we try to look for several epochs, because many galaxies in SDSS I actually observed more than once. And then basically we do Monte Carlo simulations to see whether we are significant, whether the detection is significant. So this is the filter. I won't go into details, but there's a lot of stuff starting from the fact that we clip out objects where emission lines that we're interested in, they fall onto skylines, and ending up with the relative importance of broad line versus narrow line, width of the broad line to make it symmetric, and so on and so forth. It's all complicated. It took a while to develop this sort of multi-parametric filter. It was designed to recover the known candidates, and it's also designed, like here you see the word good BPT. BPT is Bolton-Phillips-Terlevich plot for emission lines that allows you to make diagnostics where the emission lines you're looking at come from an AGN or from star formation. So we take only those that are not star formation, because it was shown that if you take in star-forming galaxies, you can get broad-line regions coming from supernova, and then they disappear after a couple of years. So, of course, there are caveats. There are shocks, but shocks are taken care of by our algorithm, because shock would affect the shapes of forbidden and recombination lines in a similar fashion. So if you have a wing, blue wing in forbidden lines, you're subtracting it off automatically by the decomposition procedure, because we're using the non-parametric recovery. So we try to choose only the candidates where X-ray was greater than, higher than what you would expect from star formation or LMXB populations. And basically, we were kind of confident that we were not grabbing supernova, because we haven't picked any of the supernova known in SDSS. Then we quickly realized that we got something interesting, and we ran the first follow-up campaign, which was 2 objects observed with Chandra DDT, 1 confirmed, and 2 objects observed with XMM-Newton DDT, also 1 confirmed. Then we followed them up using MAGE at Magellan to get the second epoch spectroscopy, and here you see the difference. This is the same object, and here you see the MAGE spectrum from Magellan and SDSS spectrum. The difference in line width corresponds to the spectral resolution difference, and you can see here the broadline region is evident. You don't even need to reduce the data to see it. Actually, you can see it on a 2D raw shell frame. So it's so bright. This is just 20 minutes of exposure. I think that this one was 3 times 20 minutes, but you can imagine. So also we did follow-up imaging, and here you see why, because this is SDSS image of a galaxy with a seeing of 1.7 arc second. This is actually the same galaxy. This is the Pan-STARRS image with a seeing of 1 arc second, and this is 4-star in the K-band with a seeing of 0.35, where you clearly see the 2 structural components rather than just a blob. Results. We identified 300 IMBH candidates with masses under 2 times 10 to the 5. Why 2 times 10 to the 5? Because the virial mass estimate is uncertain to a factor of 2, roughly. 10 of which had X-ray counterparts. 5 from literature, 4 new from archives, and 1 new from Chandra observations. We expect the cleanliness of the sample is around 70%. demographics of galaxies. They're sitting in low luminosity galaxies or galaxies with small bulges. So, for instance, this one is not a low luminosity galaxy, but it has a tiny bulge in the center, or pseudo bulge, whatever you call it. So, these are the 10 X-ray confirmed IMBH with X-ray position superimposed on optical images. So, multi-epoch spectroscopy also gave us evidence that we were not doing something crazy, because we got consistent black hole masses from several epochs. Coming back to the results, what also was interesting in the demographics is that 75% of galaxies turn to be isolated or in poor groups with 2 to 3 objects confirmed in SDSS, which goes along the lines that those are survivals from through the cosmic time, so they survived in their galaxies without much growth to mergers. So the host galaxy might have had very poor merger histories. This is the plot again, another scaling relation, mass of the bulge versus mass of the black hole, and it also has a similar meaning to the one I showed in the beginning, m sigma. Basically, it tells you that bulges and black holes co-evolve. So bulges grow by mergers, black holes grow by mergers and accretion, but mergers seem to be more important for high masses. That's why you have the correlation. In order to test this, we did our own photometric decomposition for all our candidates, and this is an example of how it works from the literature. This is a galaxy image from HST, and you do bulge disk decomposition, and you get the inner component, and this is the thing that goes to the plot. You cannot just plot the total stellar mass. We are actually going after those tiny, tiny structural components here, and sometimes they are unresolved, but we don't really need to resolve them. We need to get the magnitude or the stellar mass. And we successfully filled up this diagram, so all our candidates are residing down here on the extension, which again gives an additional argument that those are real things. Now, at the end, a few slides about the perspectives. So, IMBH are small, but sometimes powerful. We have 3 black holes in the sample, 2 in the sample of the initially identified 10, and third, which is a little bit more massive, that are accreting close to the Eddington limit. And their X-ray luminosity alone is 7 to 10 Eddington, or even 30% in one case. This is a case which I'm showing here. It's the same galaxy that was on the previous slide, for which I showed this, for which I shown the optical spectrum. And these are 2 X-ray observations from Chandra, 10 kiloseconds each. We were expecting 10 photons, and we got 500 in each of them. And it shows pretty soft spectrum. So the gamma index is 2.5, which is lower than which is higher what you expect for most AGN, which is 1.6, 1.9, and it goes along the lines with it being at high Eddington rates. We had 2 Chandra data points with good spectra, and this was the work, by the way, done by a second-year undergraduate in Moscow, supervised by Ivan. Then we had 2 more data points from Swift, and we found no variability on time scales of 1 day, 1 month, and 1 year. And this is the first idea about the duty cycle of a low mass AGN. So, finally, Monte Carlo simulations suggest that we can go as low as 30,000 solar masses, and we successfully recover the existing candidates, and we get a few more. And this was the whole idea, to get more objects of this unique type. So, of course, we have byproducts, and one of the byproducts are tidal disruption events. One of our sources has, when we took the spectrum with MAGE at Magellan, we realized that it had weird emission lines in the spectrum. So we first thought that we couldn't clean cosmic ray hits, but in fact those were highly ionized iron lines, which actually a characteristic of TDEs. And those were different emission lines that were seen 2 years prior to our observation by different people. So those lines, they're known to change over time. However, the X-ray detection that comes from Swift, it happened 2 years past the first SDSS epoch with iron lines. So we would say that the X-ray emission comes from the black hole and not from the TDE itself. And finally, the last result in a couple of minutes, it's the LX-LO relation for low mass black holes. This is the thing that was pointed out by Heckman in 2005 in hard X-ray. You see that O3 luminosity in the optical correlates with X-ray luminosity with quite a big scatter. Then it was improved, and the most recent compilation by Ueda 2015 shows much better results and lower scatter in the range 2 to 10 kiloelectron volts. We tried to build it for our objects, and we found something weird. This is a linear relation that was claimed by Ueda and Heckman, which seems to be reflecting the fact that O3 is ionized by X-ray with sort of constant efficiency, 0.7%. When we plotted galaxies with slightly larger mass range, up to 1 million, we found that the relation had a different slope. It had a slope of 0.5. So Lx was a square root of X-ray. O3 flux was a square root of X-ray flux. And it also, if you go to the masses below 600,000 solar masses, it's much tighter. So it's 0.2 dex versus 0.24 dex versus 0.8 dex difference. We don't know what it is yet. We're trying to work on it. So far, the idea is that the objects that cause it to puff up all have strong outflows, which we see in the optical spectra, like this one, this wing on the side. Well, work in progress. We have follow-up campaigns in X-ray. We have follow-up campaign in the optical. We're trying to detect rapid variability in the broadline region and the continuum and to get reverberation mass measurements for black holes. But it's all going on, and stay tuned. Within a couple of years, we'll have some updates on this. So I'll leave you with the summary, and the main takeaway point is that we conclude that the population of IMBH and AGN with masses less than 100,000 solar masses exists, and this fact disfavors massive SMBH seeds. And the fact that IMBH host galaxies possess small bulges and are located in the poor groups or in isolation supports the bulge black hole coevolution. That's it. Thank you very much.
I thought it was very interesting that you were showing us how far down you could go, something like 3 times 10 to the 4. And yet you didn't see anything in that range. Is that why you're saying that you're favoring the higher mass seeds? Or would it be possible? My question is distance related as well, because you might expect that the lower mass seeds would be in earlier galaxies.
So, yeah, here all the objects are very nearby. So it's basically redshift, it's under 0.1. And I think for 9 out of 10, it's under 0.06. So, because we simply cannot see it further. Low mass black hole has, we do the optical diagnostics, and we cannot see less massive. So, if you're talking, as I understand, you're talking about like redshift 5, 6, right? There's no way we can detect it using existing techniques because it's too faint.
So would you say then that it is possible that there were lower mass seeds?
It might be possible that there were lower mass seeds. Our detection limit from SDSS is 30,000 solar masses because of SDSS resolution, primarily, and because of SDSS depth. So if you try to run a survey, spectroscopic survey, higher resolution and higher depth, most likely you can go below. However, there's one more problem. This one, that is accreting. Where is it? I missed it. Yes, the one that is accreting at Eddington. In a few tens of million years will grow about 10 to the 5, so you won't consider it an IMBH anymore. And we were trying to think how to frame it in the like global galaxy formation and evolution picture. And it turns out that those black holes have very little sphere of influence, so they don't affect galaxy that much. And so the accretion condition, they are regulated by the host galaxy and not by the black hole, which means that it normally should be easier to feed such a black hole at the constant rate for a longer period of time than like a 10 to the 8 supermassive beast, which would just once in a while spew everything out by the jet from the center, and then you stop the accretion. So the idea is that IMBHs are very hard to find because whenever it starts accreting, it will grow. In like a 10 to the 8, you'll increase the mass by a factor of 10. So the fact that we found them is remarkable because it's a very rare and very rapid in cosmic scales evolutionary stage of black holes.
Fascinating.
One final question.
So, what I wanted to ask is that you show the black hole mass bulge mass equation. So, you computed the black hole mass using the broad line region?
Yeah.
So, what is the systematic uncertainty on that? And also for the bulge mass, how accurately can you separate bulge from the disk? And how are you going to
So,
galaxies?
bulge from the disk is hard, especially if the bulges are small. That's why we're running a follow-up campaign using...
Okay, so what would you say? What is your systematic uncertainty?
I would say that there are lots of systematics. One of them is that bulge is a factor of... The stellar mass to light ratio is uncertain to a factor of 2. Okay. So there's 0.3 dex right there. There's about 20% uncertainty from the bulge disk decomposition. So you add it to the error budget. And then there's an uncertainty on the X-ray, on the broadline region decomposition coming from the virial relation, which is 0.3 dex again. So you have uncertainties in both directions, in X and Y. So we are now working actually on this particular project, trying to fill up the mass MBH and bulge relation and MBH sigma. And hopefully we'll do the correct statistical analysis. But right now I cannot tell you, well, the uncertainties are, overall it would be like 0.5 dex here in the current situation, which is compatible with the scatter that you see in the plot. But we'll give you a more precise answer soon.
All right, let's thank Igor again. Our second speaker today is Nathan Golovich. He is currently a postdoc at Lawrence Livermore National Labs, where he's been since 2017. And currently he's working on microlensing projects, and he told me he's now also moving into looking at asteroids. He got his bachelor's in engineering physics at the University of Michigan, and then he did his PhD at UC Davis, working with David Whitman. And there he worked on emerging galaxy clusters. He primarily worked on the optical data as part of a group, but he's well-versed in a whole host of multi-wavelength observations. And today he's going to be telling us about a multi-wavelength look at emerging galaxy clusters.
Hoping I can show you what I'm going to talk about. This same thing happened when I tried this earlier, but it worked eventually. Maybe it's my DOE computer just not wanting to talk to anyone else in the world.
That's right.
Well, it's really just making use of the customer address.
I was hoping to be more blocking your view.
Go into the functions. There it is.
Sorry for the technical difficulties.
And thanks for your patience. Okay, so yes, I'm studying emerging Gaussian clusters for my PhD, which ended about a year and a half ago. And since then, I've been doing microlensing, actually looking for intermediate mass black holes at the low end of that mass range. So that was a good coincidence. And basically, in general, I'm an optical astronomer. So I'll show you my optical work for emerging Gaussian clusters. So this work was a rather large project with a lot of wavelengths and a lot of people. So I'll just point out some of them. This is definitely not all of them, but there was a lot of radio work and X-ray work done here. And this is really exciting for me to be here to talk about it because some people who were here and are here were a part of this. So I'm going to first talk about the motivation for why you might want to study a sample of emerging galaxy clusters, and then I'll show you that sample and how we built it, and then some of the data we took and how I analyzed it, and some of the key results. So the first motivation for the optical side, anyway, was self-interacting dark matter. So my advisor, David Whitman, and one of my colleagues, Will Dawson, got really excited about the bullet cluster in, 2007 or 2008. And they started wondering maybe we could find more of these and make a good constraint on dark matter. But first we needed to find a way to find the cleanest system. So these are hierarchical mergers. They are just giant beasts. They get really messy, so we want to find the clean ones. So there's also more interest. So some of the other wavelength astronomers were interested in these things, not me as much, but it ended up being a huge project, so everyone was happy with all this data, and you were able to study a lot of other things. So most of the work I'm going to show you here is from two papers that I call the sample papers. The first one was just presenting the data, the optical data, and the second one was presenting the analysis. So we needed to identify post-mergers, so we looked for radio relics. So radio relics tend to show the shock waves going through merging galaxy clusters, and thus they already merged. So I should give a shout out to Reinhardt. So this is the part of all the references for my second paper, and you can see Reinhardt van Weeren was a part of this. He was here until last year, I think. Now he's at Leiden. But the reason we want to look at radio relics also is because this is the time scale of a merger, of a simulation of a galaxy cluster growing over time, over cosmic time. And you get these radio spikes whenever there's a major merger. And if you look closely, if I could zoom in, there's like the X-ray arises before the radio. So when you find clusters that are bright in the radio, there's a little bit of a time delay. So you've given this cluster time to evolve. It's not like right at epicenter. It's not just shooting through. It's already separated a little bit. And at the time we were making this sample, this was the way we wanted to look at merging clusters, because these were like bullet clusters or a little bit older. So we started in 2012 with 8 what Will Dawson coined dissociative mergers. So these are things that have separated their gas and dark matter, and that was the term we were going with. We ended up finding this shreddy paper of radio relics with the help of Reinhardt, who pointed out that radio relics would help us trace these systems. And then we made some observational cuts. The deck of -30 was for observing from Subaru, and then we made it 31 just so we could get Abel 2744 in the sample, which was just below our cut, and we wanted it. Sorry, I should say also with the redshift, we wanted to do weak lensing on these, so we didn't want to go too low on the redshift. All right, so we took a lot of data. First, we started with some photometry, and mostly for spectroscopic targeting. So we borrowed some data from Rhino. We used SDSS, even the digitized sky survey, and also some archival Subaru Prime Cam. And we targeted thousands of spectra. I think we had 7,000 slits on 54 slit masks with Keck Demos. I was the person who looked at every single one of those galaxies, sometimes stars. And for a while, I thought I was doing more spectroscopy than anyone in the world, but I realized people were smarter and figured out how to do it a lot more optimized than I could. But in any case, that was what I did for almost a year. We found 5,400 cluster members in these 29 systems, and we also compiled all the archival data we could find. We had 38 hours on Subaru. We downloaded, I guess, almost over a month of Chandra data, and we pulled together radio from all over the place. So this really was comprehensive for all these systems. Okay, so now for the analysis. So before this ensemble study, as I said, in 2012, there was only 8 of these systems known and studied. And so basically people were getting as much data as they could for each individual system and studying them like unicorns. And I wanted to find a way to kind of pull it all together and do it at once. So I started with the spectroscopy, and basically I cut out all galaxies that were within a 5 megaparsec radius and 10,000 kilometers per second, and then I iteratively shrunk the velocity and spatial radius until we got a stable system. And so the remarkable thing about these is that they're all very single unimodal Gaussians, all except one, I guess. But here's the one, and there's reasons for that. But across the redshift space, here's all the systems that we utilized, and I'll just flip through these and show that they're all Gaussians. All of these windows are plus or minus 3 times the velocity dispersion, so you can get a sense of how massive they are by how wide they are. And they're all major mergers, so these things are merging at 1,500 kilometers per second. So if they were merging along the line of sight, you would expect to see multiple peaks on all of these, or some subset of these. So we really did get something that's showing transverse mergers already just by radio selection. The next thing we did was looked at the Subaru imaging, and so first we had to separate out the stars. So now our goal is to map out the red sequence luminosity. So we cut out stars with the with the size magnitude distribution, and then we cut out the red sequence. I was generally generous on the red sequence cut just because of all the wavelength information allowed me to rule out some of the false positives you get with that wide band. The next thing I did is the Dressler-Sheckman test, which just looks at the local deviations in velocity and velocity of all the galaxies. And if you plot it on top of the red sequence distribution that I made, you can actually start to see there's multiple clumps that trace the galaxies. The reason there's a big hole here is there's a, I think, 8th magnitude star in this field. And this is the toothbrush relic, which is one of these famous relics that many of you may have seen before. So the next thing I did is wrote a code to do Gaussian mixture models on this data, just the spectroscopic data. Looking back, I wish I had included the photometric information as well, but this did pretty well. So basically, you just generate a bunch of Gaussians, and you pick them by hand, and you get a little bit aggressive with them. So you just see an overdensity of galaxies. You say, all right, here's a place a cluster could be, and then you sample in these parameters, the covariance and the mean model, and it picks the best fit for the number of Gaussians, and then I put some constraints on it so that I don't get anything too funky, like a subcluster that's the entire cluster, or a subcluster that's got one galaxy in it, and so on. And so here's an example fit. So this is that same cluster. And so if you look at the spatial, so these colors map, so you can see that there's line of sight information and there's spatial information about all these subclusters, and they seem to track the red sequence luminosity pretty well. So on the ensemble scale, the GMM came up with 1, 2, 3, or 4 subclusters for all of these systems, and so the more messy ones are at the bottom, the cleaner ones are at the top. I will say that the ones that have one subcluster were just statistically preferred to be one, but that could be because of incomplete data. But in large part, most of them were very bimodal, and so what this plot is showing is it's the difference in line of sight velocity between the 2 subclusters that we deemed to be merging. They were generally aligned with the radio relics. Divided by the maximum velocity you expect if you put these subclusters at infinity and let them fall in. And then I put the cluster velocity dispersion on here just for reference. But the take home here is that for all the bimodal systems except one, the line of sight velocity difference is consistent with 0. or close to consistent with 0. So these things really truly are merging in the plane of the sky, and somehow radio relics are selecting that. And I guess there's one caveat. They could be at pericenter, so they could have merged at some sharp angle and reached pericenter, and perhaps radio relics are just selecting objects that are at the turnaround point. So to try to rule that out, we looked at analogs to these systems in n-body simulations. So at this point, there's these cosmological n-bodies that have huge statistical samples of galaxy clusters. And so we looked for clusters in these n-body simulations that resembled the redshift, mass, and velocity distribution of our own systems. And if you place viewers randomly within this volume, you can map out the kind of statistical probability distribution for the viewing angle of the merger axis. And so if you just place observers randomly, this gray band is where you would expect that's the random viewing angle that you get for any merger. So the bulk of the mergers are much more in the plane of the sky than you would expect just randomly. There are a couple of degenerate ones which are interesting. So one is this RxCJ1314, which address code, but in any case, it's a bimodal merger with 2 radio relics merging at a sharp angle, which is just it's pretty remarkable. Some of the other ones are these systems that I that the data were not complete enough to actually map out very well. But this dotted brown one, I believe, the dotted brown one is very interesting. But in large part, these systems really are merging in the plane of the sky. So I just wanted to lay out a couple of the ones I called the gold samples. So here's all the information that I compiled for any given system. So there's that red sequence luminosity map with the Dressler-Sheckman test, and overlaid are the radio relics. Here's the subcluster analysis. Here's the velocity distribution for the subclusters that were identified. Here's the usually Chandra information, but it could be XMM. Here's a snapshot of the cluster BCG, and then here's a little cartoon I made to what I think is the merger scenario. So these are really just, after looking at all this data from, for many months, I figured this is my best guess at what's going on. You could come up with your own hydrodynamical simulation and try to recreate something like this, and that was the hope for this. So this is Abel 1240. This is Abel 3411, which was the cover of Nature Astronomy in the first edition, thanks to Reinhardt. And here's that X-ray image that you guys may have seen. I think it was like in the lobby yesterday, but now it's gone. There's a couple other ones. So this is the sausage cluster, which was rather famous. This is one of the frontier fields. So this is one I studied in more detail. What was interesting about this is that there's this subcluster. So the frontier field, Hubble frontier fields pointed a ton of data right at the core of this cluster right in here. But I actually figured out that there's a second subcluster down here that's lost almost all of its intercluster medium after it merged through, and this radio relic is evidence that the merger happened. But the Hubble frontier field is studying all this right here, and no one's really pointed this out. And if you look at the weak lensing maps, there actually is a hint of this, but this central cluster is so massive, and they've smoothed it too much that you can't see it very well. Another one is Max 1752. This one's cool because it seems to have a little bit of a kind of curling motion. It's really hard to see in the X-ray because it's a low resolution map, but we've applied for a bunch of Chandra time this cycle. But in any case, it seems like the gas is swirling around, and this is kind of like Abel 115, if anyone's familiar with that cluster, but a little bit less dramatic. But it also has a double radio relic system, so it clearly was a mostly head-on collision, but it seems to have just missed. And if you look at the BCG, there's some strong lensing in there as well. I'm sorry. Another one is this RxCJ1314, which is that line of sight bimodal system with double radio relics. This truly is remarkable. Every other double radio relic system that I've ever encountered is almost completely transverse. The last two is Zwicky cluster 0008. This was my first cluster that I analyzed in great detail. We did weak lensing on this as well, and this really is a bimodal, very clean system. And then the last one is Zwicky cluster 1856, which we didn't have as good of optical data, but it seems to be among the most bimodal systems I've ever seen. One of the last things we did is looked at all the BCGs. So we looked at the alignment of the BCGs with the merger axis. So if you just draw a line between the centroid of the two BCGs and you measure these angles, they actually are remarkably well aligned. So And then if you look at all clusters, so there's this Nature Astronomy paper in 2017 where they looked at just all galaxy clusters in the Hubble archival database. They found that in general BCGs were aligned with their cluster, whether or not they were merging, but they're also aligned just after they merged. So it's either that the merger is aligning them very fast, maybe in the first million years, or the alignment was there before the merger. So then I'm just going to show off some of the weak lensing analyses that we've done. So this is work that's still ongoing, but here's the first few ones. So the first one we did was the sausage cluster with James G. He found these interesting offsets between the centroid of the mass and the centroid of the galaxies, kind of just at the 1 or 2 sigma level. But the whole point of our analysis was to look for this in a lot of clusters and use this to beat down the statistical noise. I'll get to that in a second. The second one was the toothbrush cluster, which there's that radio relic again. And here's if you recall, the galaxy subclusters kind of mapped the dark matter pretty well. Sorry, this was the Zwicky cluster 0008. The color scale is the mass, and the contours are the luminosity. There's Zwicky cluster 2341. You can see it's quite a messy cluster. There's also double relics on this one here, but it seems like there's a large ridge of dark matter kind of all in a stream. This is one of the most massive clusters ever detected. This is ABA 115. It's got clearly bimodal, and the gas is really cool. You can see these 2 jets. This thing's clearly spiraling in, and I know Bill Foreman was quite interested in this cluster over the years. Another thing we did was SIDM simulations. So here we take 2 clusters that have gas, dark matter, and galaxies. You put a little bit of drag force in the dark matter, slam them together, and you watch for offsets. It turns out the offsets are generally rather small, and systematic uncertainty is never going to let us get down to this level. But what did pop out is that long after coalescence, for millions or billions of years, you get this oscillation, which is rather interesting. And so the idea here is that whenever you have SIDM in the core of galaxy clusters, it gets the density distribution gets flat right in the middle. And so these BCGs are able to just wobble around without coalescing down. And I've had fleeting attempts with Ezra to try to find some free time to work on this, and I think neither of us had the free time, but hopefully while I'm here we can talk about it again. So here are conclusions. So radio relics do pick plane of the sky mergers, except that one case, especially with double relic systems, they're very clean. There's a lot of messy systems, even in the radio relic sample. The alignment of BCGs occurs really fast. This keeps happening, sorry. And it's too early to learn about SIDM from our weak lensing results, but it might be that the simulations are saying it's futile. So maybe this was kind of the big disappointment of our analysis. But there's so much interesting and rich astrophysics in these systems that we were happy to study them. So I'll take any questions you guys have.
Yeah, just curious about the alignment that you described. Is there any theoretical work saying how quickly they should align, or if you look at simulations, do you see this alignment happening?
Yeah, I haven't seen any simulations that look at it specifically like during a major merger, and that's definitely something that I would be interested in. Not sure I have time right now, but at some point I think I'd like to. Yeah, I mean, the alignment is definitely a thing that shows up everywhere. I mean, if you look at galaxy clusters, you can see alignments between the BCGs of nearby galaxy clusters. So galaxy clusters are embedded in the cosmic web, and there seems to be some primordial alignment as things grow. But we weren't quite sure how to interpret this beyond what I've said. It's just either the alignment's happening really fast or it was already planned.
Thanks.
I don't know if you have a chance to look at this yet, but there was a paper, Nature or Science paper years ago. I don't remember exact years, but they looked at something clusters in the Hubble data, and they observed some displacement between the weak lensing centroid and the galaxy centroid and X-rays. And based on that, they actually placed some constraints on the cells interacting.
I'm glad you bring it up. I avoided doing this. So we submitted a rebuttal of that paper and showed that with more comprehensive data, their signal is gone, or their constraining power is gone. David Whitman was the lead author of our rebuttal. You can check it out. But in any case, basically, they used single band photometry, and they tied a lot of spurious peaks, and we found that what was driving the result was just a handful of clusters. Out of those 70-some, there's only a couple that were driving it, and they were a lot of it in large part errant. So we looked at the offsets in the more comprehensive data sets that they ignored, and their constraint dropped down to like 2 centimeters squared per gram, which is not even better than the bullet cluster by itself. So
Any final questions?
Who's the cluster that had the relics and also the velocity, 2 velocity peaks?
yes, that's.
So how can that be?
So are you talking about the double relics with the line of sight, or the two? Oh yeah, the 2 velocity peaks. That is Abel 781.
Yeah.
That is because it's a rather messy. So this one. Yeah.
So you have a picture of it where we can see the relics and.
Yeah, 1 second. I don't have any. Okay, effectively, I can explain it. So there are 4 subclusters. It's one of the messiest ones, and there's just a merger going on, and then other stuff all around. So it's just a really messy system.
So in principle, can you tell that the relics come from 2 clumps in the plane of the sky, and that the velocity peaks come from things perpendicular?
Yeah. So here's the expected. So out of the 2 subclusters that I interpreted to be merging, they seem to be close to the plane of the sky, but the 2 peaks you see in the velocity distribution are unrelated, or not part of the merger. This cluster was in the Shell's spectroscopic survey, so it actually had like 800 subclusters, or 800 spectroscopic redshifts to work with. It's pretty impressive.
Okay. I wanted to mention that Nate will be here today and tomorrow, so if you're interested in talking with him, come up or email me. Let's thank him again.